Today we are with Julian Lienhard in this series of lectures on lightweight pioneers. We like to look back at some of our recent history, a century old, just to do not forget in our very easy modeling environments that there is a link between geometry and lightweightness, and it's always very good to see this relationship, especially and notably the cases of those pioneers who were inventing methods for form finding and for calculating, and they were really triggered by this by this geometrical challenge. And we are very happy that Julian, who we never invite him to do this type of lecture, is joining us today. Okay, it will be our guest faculty teacher in the second semester in Studio 2, but we are very pleased that he is today with us. He's a director of the Institute of Structural Design at the University of Kassel, and so he's a very good engineer. He's a managing partner of a very cool and young office structure in Stuttgart. But basically, we like very much from him his very simple analysis, but very very powerful views of linking form finding and structural design. And we are also very pleased. I'm very thankful for all his effort writing down his thesis and settling the foundation of the bending active structure framework. Even though it's like very exotic, it is very beautiful. So thank you very much for coming. And Julian, we are very good to listen to your presentation.
Great. Yeah, thank you for the invitation and a cool poster. Yeah, so maybe before I start my presentation, I will just give you a tiny bit of background. I studied civil engineering in Stuttgart and was quite fascinated by the Institute of Frei Otto very early on. And so I decided to work as close as possible to him, and then signed up as a student to an architecture office in Stuttgart called SL-Rasch by Bodo Rasch, who is the lead architect who realized a lot of large convertible membrane structures in the Middle East. So some of you may be coming from that area, and then you would know these umbrella shades in front of the Medina Mosque. And all of these were developed in co-development with Frei Otto. And in the office where I was working, then Frei Otto was still an advisor. So I had the rare chance before he became blind to actually also work with him. We visited him together with students sometimes when I was a PhD. So I got a bit of hands-on experience understanding the way he thinks. And so what I'm going to do today is I will not so much talk about him as a person and all his kind of the history of his developments. I talked to Enrique. There's this pretty good film documentary on him online. I guess Enrique said that it was already shared with you. So if you haven't seen it already, then you should definitely look at it. Maybe Enrique, you were going like this. Maybe you can send them the link.
Yeah. No, it hasn't been shared yet. Yeah, but definitely.
Okay.
Will do.
So in that documentary, you will hear him talk. You will see him working with the models, and you will see some architects talking about his work. It's as Enrique rightfully said, there's a lot of Zaha Hadid talking about Frei Otto. So it has a specific take on his work, but I think it's the most complete documentary with excellent footage of all the work that they were doing. So what I'll do today is I'll actually do exactly what Enrique was saying. I will show you a bit how his way of thinking and the way they were doing research through observation and breaking it down to very simple rules, how that's influenced our whole profession. And I'll show you partially the historic work and then also show you a bit how we work with this knowledge today. that was my idea, and I'm realizing my office is super cold. We have this
shortage in gas.
We have this idea in Germany now that we have to really save on energy, which is a good thing. But
wear more clothes.
Yeah. I'm about to put on my jacket. I just came in from another lecture. I'll just start by sharing my screen, and then we'll kick off with this. If you can just give me a thumbs up if you see everything correctly.
Perfectly.
Okay. All right. So this is him. This is him in the early days, standing on one of the mock-up prototypes for the World Exhibition in Montreal. And so this photo might actually be in Montreal. I think it is in Montreal at the World Exhibition. And I will talk a bit about the developments that led to this amazing breakthrough of this World Exhibition, because this is really the moment when he became very known on an international platform. I'm sure you've seen a lot of these images. So this is what he's generally associated with, the work at his Institute of Lightweight Structures, where they were developing understandings about about the connection of geometry and structural behavior, essentially through model building and experimental workshops, working with partially super creative, looking into nature, looking into just creative experiments and seeing what happens, and then partially also working extremely scientifically with these models to really measure down to very high precision the exact geometries and the exact relationships. And so if I just go back, there was 3/4 main fields which he was focusing on. The one field was textile membrane structures, and you can split that into two. There's the mechanically pre-stressed membranes, which is kind of this world here, and then there's also the trying to get to my laser pointer. Voila. There's the mechanically pre-stressed membranes. That's kind of this world. And then there's the pneumatically pre-stressed membranes. That's when you put air pressure inside it. That's where they were also doing experiments and working more on this world. So that was the first one or two subjects, the textile membrane structures. Another subject that he was focusing on, that was actually quite in the beginning of the work, that's actually also the first IL publication, is these branched structures, where also they were looking into how can you catch a large aerial force and bring it down to a point. So we're also studying systems in nature, mathematical rules, different experiments that they could do to derive these kind of shapes. And then the fourth subject is that of shells, and then predominantly grid shells, which they were studying. And that's, I guess, something that you guys will be looking at quite intensely. So I will actually also talk about these four fields. I will talk a little bit about membrane structures, pneumatic systems, the branch systems, and at the end, I will keep it quite short and outlook into the grid shells, because I guess there you have much better experts than myself at your hand with Enrique, so I don't need to talk too much about that. So let's look into membrane structures, and then when you see the image of Montreal, of that World Exhibition Pavilion, or when you see the Olympic Stadium of Munich, and a lot of people said, oh, they were probably looking into nature and then translated, for example, spider nets into something architectural. And to Frei Otto, it was always very important to point out that they didn't actually mimic spider nets, but it's because they built Montreal and Munich that biologists approached them and said, oh, you seem to have a very good understanding about these kind of systems. Can you explain to us how spider webs work? So there's this obvious link. Yeah, you look at these systems and then you look at an image of Montreal and then you think, wow, they've just built a spider web. But this system that they built in Montreal and these cable nets, that came out of a totally different idea, and it just happened to look similar. And then when you look at it in a bit more detail, you also actually realize that in the way these spider webs are built, they are actually quite different to these cable nets. But there seems to be this link. And because the spider web is also a pre-stressed system that's tensioned under its own weight or pre-stressed during the construction when the spider is making the web, and it's hanging under dead load and it's turning into a kind of surface structure, you see some properties of this net which we recognize from these tensile membrane structures. You see this double curvature. You see that it's becoming actually a lot more dense around these local points, something to do with the concentration of forces. And I guess through trial and error and through too many meshes breaking, the spiders have learned to make their nets a little bit more dense around these areas. But as I said, it's not actually the team around Frei Otto looking into nature and then saying, let's build something like a spider web, but it came from a different understanding, which I'll share with you in a minute, that then led to biologists approaching him and saying, can we learn more about these principles? And it was actually in this dialogue that they started then working more and more with people from other disciplines. And in later large research projects, they got funding for architects, engineers, and biologists. So they could work in this world of biomimicry or bionics and actually address their work at these translations between natural phenomena, which you find in plants and animals, and then translating that into something technical. Now, if you look at textiles as a material that we can use to build envelopes, you could say, well, we have a thousands of years old history. Some of that history of building these tents has lasted until very recently, which you find in North America and North Europe. And some of it we can date back to the time when most of the people on our planet were nomads, and then they would build these very light systems. Where in that case, they would take a structure out of timber, just cross-connecting something they could find anywhere in nature, and then cladding it with textiles. In the beginning, that would have been animal skins, and later it would develop into woven textiles. And we see in other regions of this world, we see that the primary structure, so the timber that they need to build these, would become more rare. So in the northern tundra or in areas in the northern European or North American forests, you would have timber as an almost endless resource. Whereas in the more desert areas in North Africa, timber is actually something that's very scarce. But what they did have is goats, and they would have wool, and they could start weaving wool into skins. So they could build tents where they would rely a lot more heavily on ideas, which minimize the amount of structure that they put into it to create this kind of enclosure. And that then actually leads to something where we can see a very clear difference between what we mean by textile as a cladding material and a tensile membrane structure. So in the top example, which I was just explaining here now, the different example of just some wooden rods being put to a point, and you can see the structure is freestanding, and then they apply the textile as a cladding. This is not what we mean by membrane structures. Because when we talk about tensile membrane structures, then we talk about something where the membrane plays an integral part of the structural system. And then you can see in this nomad tent that actually in this case where there was a bigger pressure on building something lightweight, reducing the amount of material that goes into it, that you now see that, for example, the central post without that woolen membrane being pulled over it, that post would fall over. So there's a degree of integration here between the skin and the structural system. And immediately you also see in these drawings that we see some curvature appearing on the surface. So the people making these drawings, they were not architects or engineers trying to explain something about curvature, but you also see it in this image just through observation. When they start tensioning these skins, then there's some curvature that appears. And this is actually a very central part, and this is kind of the first observation that then leads to the work of Frei Otto and this idea of building something structural out of a textile material. And it's quite interesting when you look at the image below from 1955. So this would have been a German gardening exhibition. That's an event that happens every 2 years in Germany. And for some time, that was always the moment when people were exhibiting next to the gardens that were built in the cities. They would also exhibit some kind of new architectural explorations. And Frei Otto actually became quite associated with these gardening exhibitions and would always show the latest developments. And when you see a sail like this, every one of you has seen it many times. And actually, in some parts of the world, you can just go to the Home Depot store or the local hardware store and just buy one of these to put over your terrace. And we totally accept that, yeah, why not? We can just span a piece of cloth like this. It's quite interesting, in 1955, people were seriously doubting that this can be a structural system that will not fail. There were some quite known engineers that were not working around Frei Otto that said, this is a material that cannot take compression forces. It's a purely textile material, and you're wanting to just jack it up with these posts in the corners. If there's wind catching into the sail, this entire thing will collapse. And it's now just 80 years later that we've totally find it the most normal thing that we can build tensile membrane structures like this. And it was actually a very important part in the first work of Frei Otto in his dissertation that where he was focusing on the hanging roof, a large hanging roof structure, which you would mainly see in halls. And in his understanding of how forces work in the system, that became kind of the first stepping stone in this theory of tensile membrane structures. And that's what then led to these kind of sails and sail structures, and then to all the developments that happened afterwards. All of this is based on an understanding of how pre-stressed systems work and how cables that are crossing in a pre-stressed manner, how they can be stable against any external loads. So this is actually a central part of his work in his first dissertation in the Hanging Roof book, where he delivers a theory and an understanding that you can mimic with model building, which then leads to an understanding of how these systems work. And we will actually now just take a few minutes to focus in on this a little bit more, because it's, as Enrique said, it's these very simple and basic pieces of understanding about forces and form, which totally open up a world for you to understand how you can design creatively with these kind of systems. So I'll be looking into these graphics in a bit more detail. Before then, I want to just put in from the side, and early on I could only find the German graph to it, but I'll quickly translate it for you. I put in from the side something that was historically super important. And that is that at the same time as Frei Otto was developing this understanding about how tensile membrane structures could work, or how tensile systems work themselves, the petrochemical industry at that time was developing new materials. And and in the beginning, we know the early explorations of Frei Otto, the membranes were predominantly built out of cotton, and then some mixed cotton and PET fibers. And there, the strength of the material is very limited. And it's only because of PET being developed further and then eventually glass fibers as a material that he could source as a membrane material, that he could suddenly get into this world of these large span tensile structures. Without this material development, which just coincidentally happened to happen at the same time, without that, it would have been impossible to push the boundary in the way he did. And he himself developed a lot of ways of looking at material and their properties. And the one thing that was first suggested at the IL is the so-called rip length. And with this rip length, they were studying materials, and they were always putting the weight of the material against the strength. So you have a material that has a weight. I'm just going to take my pen here. Blah. You could say you have a weight of a material that's given with, for example, take timber, maybe 5 kilonewton per cubic meter. And then timber would maybe have a strength, just as a normal typical timber that you could buy. That's not a high-ranking glulam. It would maybe be 1.5 kilonewton per square meter. And now, if you put in these two numbers into a relation, then you can find out what is the maximum length of a piece of timber that can hang under its own weight before it rips. So it has the property that it has a certain strength, and it has another property that it has a certain weight. And now if you compare these two numbers about how strong is it and how much does it weigh, you can then calculate, you can just imagine an endlessly high tower, and then you hang a steel fiber on that tower, and you hang a timber fiber on that tower, and then you hang different kinds of fibers on that tower. And then you actually see that steel has a shorter rip length than timber, for example. Even though steel is 10 times stronger, it's also 100 times more heavy. So in that case, it would then rip much sooner. And then you can see that there's some materials like the PET fiber, they combine high strength and low weight. And especially then if you go, this would be carbon fiber and glass fiber, there you suddenly have a material in hand which is super light and has an extremely high tensile strength. And this is essential because if you look at a membrane, you need to combine a lot of properties. So you can even start thinking about building something out of a textile that spans over 20, 30 meters. So now we talked about we need a high strength. We need a high elongation at rupture. So carbon fibers, they almost have no stretch and then they suddenly break. Whereas glass fibers and PET fibers, they have a bit of stretch in them before they break. And it was also an important property, just like if you have a stretch shirt that you're wearing, that if they would build these membranes, they would produce them too small so they can stretch them into shape, and that gives them their stability. So fibers that are super stiff also wouldn't have worked. And then it really comes down to these two fibers which can be used because they combine high strength, low weight, also with a low stiffness. And then there's actually very few materials left that have a very high strength and a very low stiffness. And in that, you then get enough stretch out of the material so you can really pre-stress it. Of course, UV stability is important, resistance against water. You would have to be somewhat a little bit of fire protection has to be considered. It at least mustn't melt and drip down as kind of molten plastic on the people. So then there's a lot of other properties which also X out a lot of the other material options. And so you can see that actually out of the abundance of material developments that are always happening, there's still to today, there's only 2/3 fibers which are left, which we can use for these applications. And they were all three of them, PET, glass fiber, and then PTFE. Those three fibers were predominantly developed just at the time in the 60s, 70s, when Frei Otto was starting to build these roofs. So that's kind of the small sidekick, that it's not only him pushing the agenda, but it's also coinciding with the material developments that the petrochemical industry were doing at the time. So now let's go back and look at this principle in the way Frei Otto explains how forces work in this system. And he explained it in a very simple model. You saw the drawings earlier on where he said, I can take two fibers that are crossing each other. You could imagine in his sail that he was building a really large membrane roof. And you have the two crossing directions inside it. And you could focus into it and say, I'm building a model just of two fibers crossing each other within my membrane structures. Or if you want to imagine it a bit larger, this could be a cable net, for example. And as I'm tensioning this net or this membrane from the four corners, I'm putting tension into the surface. And now I want to observe what's happening inside the surface. So you could build a model just by hanging a string, crossing it with another string. And then you can observe that you can pull down and you can pull up. And there's always one of the strings which becomes active as you pull on it. And it's because of this crossing string behavior that we actually now have a structural system built out of materials that can only take tension forces, yet it's stable against loads from any kind of directions. And it's, as you see it now, I'm sure for most of you, it should be super logic right now when you explain it like this. And this was actually the great talent that they had, that they could really break it down into super simple, very physical explanations. And then when you understand this, you can scale back out into the complex systems, and you always have that in the back of your head. We could focus into it a little bit more and now look at the way you can explain the same thing through graphic statics. I'm sure I have a kind of mix of architects and maybe some engineers. Maybe some of you have never heard about graphic statics. Maybe others had to go through it in university for many semesters. So I'll try and explain it very simple. For some of you, it may be a bit fast. For others, it may be a bit slow. So let's just take a second and really understand what they were proposing here. So we again have this crossing fibers of the membrane. And what I'm doing here now, I'm putting these two gray surfaces in it so you can just read it a little bit better. So really, this is the two fibers that are crossing each other. There's one which we call the standing fiber. That's the one I was just drawing. And then there's the hanging fiber, which is this one. And then you can say in any system, we have equilibrium if the addition of all the forces that you can write into the systems, they add up to zero. That's Newton's third axiom, that actio equals reactio, so that all the forces on the system outbalance each other. And in graphic statics, what you can do is you can find the resultant force of force vectors. And so the theory that we need to find now is that the reaction force pulling up from this one cable, maybe I'll actually quickly change the color so it just becomes a little bit clearer, against the other force pulling down, that these two forces, they, if we add them up, they need to add up to zero. And this you can do by just checking if you look at the force as a vector. So we now look at the force inside that cable or inside that fiber within the membrane, we can draw it. The direction of this error is given by that angle. Yeah. and the length of that error is given by the force. Then we take these two forces and we add them. In graphic statics, you always add the forces head to tail, and then you can close the force diagram, and that's what gives you the resultant force. Then you do the same in the other direction. I'm just drawing over it to just make it a little bit more clear. That was not very clear. I'm using a pad where I can't see what I'm doing until it appears on the screen. So bear with me if it's not super sharp, but I guess you can already see where I'm heading. That in this case, the same thing happens in the opposite direction. Now my pad has lost its direction. Now you see, in this case, the two resultant vectors are of the same size in opposite direction. So according to Newton, we have equilibrium. And that's what Frei Otto was arguing with this drawings, that he said that we can draw equilibrium at the one node within our textile system. And if we can prove it there, then it's also true for the rest of the system. And if you look carefully at this drawing, this was only true because I was drawing it in a way that the lengths of the vectors 1 and 2 were the same, and the angles at which I was drawing it were also the same. So now you could ask yourself, what would actually happen if I pull on the one string a bit more than I pull on the other? I guess I could still find equilibrium. And this is what this next drawing would show you. That you now say, well, right now I want to pull more in this direction of the vector v2. Well, I'm just going to switch to the laser pointer. Might make it a bit easier. So now I'm pulling harder on this string in the v2 direction than I'm pulling in the v1 direction. And because I'm pulling harder on it, I can represent this by an arrow which I draw longer. Because in graphic statics, the length of the vector represents the force. And then through observation, I can see I could build this out of rubber bands, and I would immediately see, all right, this point has also moved up. That's what we would intuitively say anyway, right? If you have these two crossing fibers and we pull more in one direction, then obviously it would pull up higher. And then if you put that back into graphic statics, now V1 is smaller than V2, but at the same time, we've changed the angle, so alpha is bigger than beta. And it's because of these two things changing at the same time that the two resultant vectors are still of the same size and in opposite direction. So we still have equilibrium. And what I was just saying here is that geometry is connected to forces, and that I cannot change the one without the other. And this is kind of, if you can understand this, then you understand the entire work of what Frei Otto and the whole lightweight movement was heading for, that they were looking at systems where if through change of the forces, you influence the geometry, and if you change the geometry, you will get an effect in the forces. And this is basically, in terms of graphic statics, with this super simple explanation, what's explained here. And then finally, you can say, well, if I now have external loads, then you can also see that an external load would lead to a deformation of the system. That again would change the angles. And then the resultant vector R1 would reduce so much until F plus R1 again equal R2. So it's the resultant vector in the opposite direction catches not the entire force. So R2 doesn't have to stand against the entire force of F1, but R1, which points in the same direction, actually helps virtually carrying this load, which is kind of strange, right? Because we just said in the system, it's always the hanging direction carrying the loads that are working vertically downwards, and it's the standing direction that carries the loads working vertically upwards. But in this graph, they could see that actually if I pre-tension the system, then I can actually put into an element that can only take tension forces. I can add some compression force to it, and it will carry that until it's lost in entire pre-stress. So again, with just a basic argument, they could develop a theory around this to understand how pre-stress systems, by pre-tensioning them, they would become stable against any external loads. And it's that what's needed to explain why this would be standing. Now, this is why in 1955, Otto and his team could build this roof and be 100% sure that there can be any wind, any snow from any direction, and this thing will never fail. Okay, so that's the first fun theory that I can share about Frei Otto, and that's kind of the starting point, how we got into this whole thing. So what we can, if we just go back one, maybe here. So if we can understand this was his first theory, then we understand that we can build something that's structurally sound, so stable against external forces from any direction, out of a material that can only take tension. And we can see that force and geometry is inseparable in these systems. You cannot talk about force without talking about geometry. I will jump over this, and so basically these graphs, I will share this presentation later, they just talk about the importance of curvature and how increasing curvature in these systems, obviously, if you have these two crossing fiber directions, if you translate that back into the surface, we are then talking about double curvature. And then you can see how the double curvature influences the amount of deformation that you get in a system. So a totally flat sail, which you see at the top, would have 100% deformation. Then a highly double curved one would gradually reduce the deformation. And then by this curve being nonlinear, you can also see that there's a kind of sweet spot between between how much curvature you need to add into the system. So with this theoretical understanding, they would apply that then to model building and try to develop shapes through these form finding models that they would build. And an important method to build these form finding models was that of using soap film. And that again is something that can be argued very logically why you would use soap film to develop a membrane system. So just now we were talking about force equilibria. And this is a totally different argument where they say, well, let's try and find a way of experimentally developing these surfaces. And the property of soap film is that it has a surface tension and thereby is self-contracting. That's always, you could, as an image, you could always imagine it's always trying to be as thick as possible. So as it's contracting and gathering material to reach maximum thickness, it can do this only if it's minimizing the amount of surface area. You need to take this material from somewhere, right? I'm just going to take something against the cough. So I've been lecturing since 8 o'clock this morning and I had half an hour break. So I'm kind of losing my voice a bit. But not on such nice subjects where you can just show amazing images. So the argument is I'm using a material that's self-contracting, thereby maximizing its thickness and minimizing its surface area. The result, what we get, is that we form find the minimum surface or the minimal surface. I'm sure that's something that you've heard. Minimal surface is basically just that surface with the smallest amount of surface area between the given boundary conditions. So if this is my boundary condition of the arch, and then I have some edge cables, And I could draw any surface in between here. I could draw some kind of shell surface. I could even, draw something that's undulating or whatever you want. And all of these would be viable surfaces within these boundary conditions. And there's only one surface which has the minimum surface area. And this is actually an excellent argument for a membrane structure for two reasons. First of all, the idea was to work with the least amount of material, lightweight structures. So we might as well build the smallest surface that we can build. Right? If there's a theory for it, that we can find the minimal surface, let's do that. That's the smallest amount of material that I can use to cover something. But there's also a really good structural reason, and that's always something that Frei Otto would argue for. And that is that if I build the smallest possible surface, then any external load can only lead to tension. Because if you visualize that for a minute, that any external load will obviously lead to some kind of deformation of the surface. And then that deformed surface is still one of the surfaces that you can describe between the boundary conditions. But there's only one minimal surface. So any other surface that gets generated through deformation must be bigger. And bigger means elongation, and elongation means tension. And that's what I want to do with my material. So it's actually, it's a totally clear argument if you try and understand it like this, to just say, oh, I have a task to build something out of a material that it can only take tension. Well, then let's build the smallest amount of surface area. So whatever happens to it, it can only react by stretching. And it's because of this that they then started building all these different model building tools so they could build surfaces out of soap film. They built this amazing machine. And inside this machine, they would build all these membrane structures, dip it in soap. There was a high humidity within this machine and a glass in front of which they could take photos of their membrane structures. And then they would measure the coordinates on these photos so they could then get a geometrical understanding that's reproducible of these kind of surfaces. And it's still today, some of the form finding tools reference this and say it's the soap film method. And there's big debates in the industry whether that's actually the best membrane surface or not. There's some companies which say, well, these minimal surfaces, they have the property that they become very flat around the corners or in the center. And that's why it's maybe not such a good idea to build them. But because this comes in Frei Otto's philosophy, this comes out of the idea of finding the minimal. He would always only try and find ways to build these minimal surfaces, and then to control the geometry within these surfaces, he would add additional cables to it. These so-called ridge or valley cables. And then with these ridge or valley cables, he could then make the surface into smaller zones, and that would then again control against something being too flat. And actually around Stuttgart, in the Stuttgart area, there's some offices which only work with this method. And then there's other offices which will never work with this method and always work with tension that differs in the two directions. And then they have big arguments at some of the conferences and try and find out what's better or what's worse. It's quite interesting that still today there seems to be a debate about it. Quick excursion to the side. We talked about minimal surfaces. The property of a minimal surface is that the mean curvature is, if you measure it, that the radii are the same in the two opposite directions, which leads back to that argument. If the two radii are the same in opposite direction, then it leads back to the same argument as we were doing with graphic statics earlier on. And then you can look at mathematical minimal surfaces. So when you guys are developing your own designs, sometimes it's quite good to look at these math home pages and see what kind of definitions there are of these amazing minimal surfaces. And then you can either try and mimic this or build this as a sculpture, or you can see that you can actually build a section of this as part of whatever you're trying to design, right? So there's kind of quite exciting surfaces that lie within that. They could just become a source of inspiration. What they would do then is to always play between these physical models where they would tension textiles at a very certain model building strategy. And that is that usually you tension a large piece of textile over your entire model. Then you try and rip it up, pull it up a bit so you equalize the tension in it. And only then you fix it around the edges, you add in the edge cables, and then at the very last step, you cut out the borders. It's the last thing that you do. With this method, they could very quickly build these kind of surfaces. Yeah, just some impressions of that. And then some of the basic membrane shapes that you can then build based on this philosophy. And then you actually see that at the end, it's actually very few types of membranes that can come out of this. This image might suggest there's an endless amount of types of membrane structures that you can build, but it actually narrows down to 3 or 4 types. And those are the types that we call sails. Sails are defined by just their corner points. And this is a kind of hybrid between a sail and a ridge and valley system. This is a valley cable, because you're inside the valley here if you're standing there. And this is a ridge cable, because if you're standing on there, it's like standing on the ridge of a mountain. And the first type would be any kind of sail that's pulled between more than 4 points in space. And then the second type would be a ridge and valley cable structure. You can build sections of it or entire structures, and a large part of the form finding relies on the tension in these ridge or valley cables. That's how you can control the surface. Right? That's also another sample of a ridge and valley cable. Then you have this family of high points and low points, where if you take like a very standard membrane roof, you would build maybe something like this. You could put it on a mast, and then this would be your membrane roof. And then you can also invert that and say, well, I can also build an umbrella. That's just the same principle. I'm pulling 1 point out of the surface as a low point. There's a second formula. If we now look back at these systems, then now we've understood a little bit about the surface, and we can have a very short excursion into understanding what's happening around the edges here. And there as well, in one of the IL books, they first proposed a formula which describes the relationship between the tension in the edge of a membrane. Where's my pen? There it is. So that would be the pre-stress of the membrane. And then you have a cable that's pulling on it to the side. Would be the cable force, and you can describe the curvature through a radius. And then the basic formula is that if I have pre-stress with the units kilonewton per meter, and I have a radius with the units meter, and I'm trying to find out what's the edge cable force if I have a given pre-stress in the membrane and I have a given curvature, then you can write this very simple formula that kilonewton equals meter times kilonewton per meter. Then these two X out, and then you end up with this formula. Again, a super simple breakdown of what's happening in this edge. And again, this is connecting geometry with forces, right? So with this basic formula, you can just say the radius and the pre-stress have an influence on the force in the edge cable. Now, if I try to build a membrane structure and my task is that I have a courtyard which I want to cover, then my first idea could be, well, then let's build a membrane structure that looks like this with an almost straight edge. In this case, the radius would be infinitely high, right? Of a straight line, the radius is infinitely high. if I put in infinity or a super high number into radius in this formula, then I also get an infinitely high edge cable force. It's not a very good idea to try and build a membrane with a straight edge. Then I could say, oh, I want to work with really small forces, so let's build this membrane. And then you architects would say, well, it looks funny, but it's totally defying the point because we were trying to build a roof and not some kind of fancy sculpture. So it would be interesting to see where in between the straight edge and the very curved edge, where there's a point where it makes sense to build these kind of roofs and to find out what the optimum edge cable radius is. And you can find this out if you say, instead of the radius, I'm putting into this formula the relationship between span and sag. So each edge has a span L and a sag, and that's connected to the radius. So on this graph, what we have, if we have 0 as a relationship between span and sag, we have this straight line. So somewhere down here on the left, I have a straight line. And then here, if I have 0.5, I have half a circle. And it's interesting to see that if I then put this into a plot, then I can see obviously in a straight line, the forces are infinitely high. So that never actually stops this line, becomes a vertical line. And then down here, I can see that the forces is not really reducing anymore. So at some point between 10 and 20% span and sag, in this kind of geometry, we have the optimum relationship between force and form. That's why in most membrane form finding softwares, the presetting is that the edge cable has 10% sag. It's when you switch on these commercial form finding softwares, they will suggest this value. And the reason is the super simple formula, again, first suggested in one of the first IL books by Otto and his team, connecting that to some basic geometry and just saying, okay, if we plot these, then we find out these are the type of membrane structures that we should build. And then if you have this basic understanding, the connection between radii and forces, you can also start playing with it. And this is something that we, for example, did around the teams of Frei Otto for these Medina umbrellas. First in the early 60s, these first funnel umbrellas were built in Cologne with Frei Otto. And if you build convertible umbrellas, you want them in this closed state to be as slender as possible. And at the same time, we've just learned that if I now would build this umbrella with just 3 arms, and I have a span to sag ratio of 10%, then I would be building this umbrella, and this entire area would not be shaded. And we've also learned that instead of that, making a straight line would lead to super high forces. So what we do is we break down the edge into more points where we can then have smaller radii. So we push into a higher shaded system. And instead of then pulling back with each one of these points into the center, where I then need a lot of steel, and then this package here will become very thick, I instead of that use these so-called passive arms, which I'm connecting to the umbrella with hinges, and that just passively push out the edge. Now, this is only possible if the force that comes in from the membrane perfectly points in the direction of these arms. And this is something that you can actually see here. If you look at the edge of the membrane, you can see that this edge has a different curvature to this one. Right? You can actually see the connection between force and form here. So if we now draw that into the system, we take these radii. From the radii, if force equals radius times pre-stress, then the radius can be directly connected to the force. So I can add the force diagram again, add up the vectors like we did in the beginning, and through graphic statics, I can find the resulting direction. And then even on this photograph, I can show you that the force is pointing in the direction of the arm. And you can see here, again, in this photo, you can see this inseparable relationship between form and force, you as an architect, you cannot say, oh, but I would prefer if these edge curves would be the same. And it would look nicer. That wouldn't work in terms of forces. Right? So you can actually see what we're talking about in terms of relationship between form and force. You see it in all these systems, sometimes a little bit hidden, like in the way I've just shown you. How much time do we have?
As much as you want.
Okay. I'll take maybe another half an hour. Is that okay?
Yeah, 25 minutes.
Okay. Now, earlier on, I was explaining you about the search for the right material, that we need a fiber material that can be stretched as we build the membrane structure out of it. So when you're able to form find today on a computer, and back then in soap film or in textiles, you're able to form find these surfaces. And these are doubly curved, and they're not developable. So you can't just put them flat on the ground. So now you need a theory of how to cut them into strips, and from these strips reassemble the double curved surface. A very simple way of cutting this strip would be by triangulation. If you do that in 3D, so any triangle is flat, and you could draw a 3D. Somehow my mouse is lacking a bit. Oh, whoop. So you could draw the triangles in 3D here, and then reassemble them in the flat, right? So that would be a very simple geometric method that you can do on your computer. At the same time, the argument is still for minimal material. So if these pieces of textile are being produced on a roll that have a certain width, that's the production of a piece of membrane, maybe 2.5 meters wide, then our aim is that we want to find a method of making these cutting patterns where the patch which I'm cutting out of the membrane is perfectly straight around the center line and has the width that fully exploits the material that I'm working with. So the theory that they then developed was saying, well, what I'm actually looking for is a straight line in my cutting pattern. And the argument is then, if I have a straight line in my cutting pattern that's connecting these 2 points, then that's the shortest distance on the surface between the 2 points. Because if in 2D, the shortest distance between 2 points is a straight line, and then in 3D, the shortest distance is what's called the geodesic curve. So they were actually looking for geodesic curves along the surface because that's a straight line. And around that center line, you can then develop the cutting pattern, knowing that it would end up being straight. Because any cutting pattern that you would just do with the Rhino command unroll, that you cut somehow out of the surface, would end up maybe being skew like this, and then you have a lot of material that you would cut away and waste. So also here, and this reappears in all the texts that we're writing and all the experiments that they were doing. You always see that what they were trying to do is finding the minimal amount of material. In these models they were building, they would then just simply use rubber bands and stretch them across the surface, and then mark the areas across these rubber bands, and then say, okay, this is our cutting lines. Because I know if I follow this line and I develop and I unroll it, then I would end up with the minimum off-cut in the membranes. I wouldn't waste so much material. And so you find funny pictures of them somehow trying to 3D rationalize these complex shapes into something that I could write down 2D, right? That's something that we don't really have to do anymore today. I will jump over this excursion into more cutting patterns and just say a few more words about pneumatic systems. So I was saying that there's these kind of 3 subjects, 3.5 subjects, the tensile membrane structures, the branch systems and the shells, and the tensile membrane structures in Otto's books generally get divided into mechanically pre-stressed membranes. That's what we were looking at just now. And the pneumatically pre-stressed membranes that's what we're looking at next. These can be divided into some very basic families. This is what you know from your air mattress. You can build these air pressure compartments, add them side by side. You can build cushions that are fixated between edges, or you can build so-called air holes where you have a piece of membrane that's touching the ground and then you blow air into it. And again, there's a very basic theory that goes with it through observation of, I'm just realizing that you just check whether oh no, there's something got missing, or has it moved back? No, indeed, there's, I had some old images of Frei Otto's first experiments. We'll jump over them. We anyway are short for time. So through their observations with all these soap bubbles, I would have been able to show you a few more soap bubble images of these first experiments. They saw that it would always tend to become a sphere. Whatever you do and put air pressure into it, it would have the tendency to become spherical. And then the way that you can argue that this can carry external loads if you build a kind of cushion is that you have a high pressure inside this cushion, and this forces perpendicular on the surface, they lead to a tension within the surface. And if you now apply external load, then this gets passed through the air pressure onto the bottom membrane, and that's what actually carries the loads. So it's quite interesting for you to imagine that if you see the next ETFE structure and you see snow lying on it, then you need to imagine that the structural member that's carrying the snow is not the one that's touching the snow, right? Because the force gets passed through by air pressure onto this lower cushion, and that's what's actually carrying the weight. And here again, they could derive this very basic formula of connecting force and geometry and just saying that the stress in one of these cushions is equal to 0.5 times the inner pressure times the curvature. And again, you can draw this graph and say, if I have no curvature, so if I have a flat cushion and I try to pump it up with air, the stress in the membrane would be infinitely high. And if I then slowly blow up the bubble into the sphere, then the forces become smaller and smaller. And again, in this relationship here now of sag to span ratio is about 10%. That's kind of an area where these systems operate quite economically. And then with that, you see all these modern and traditional structures that were being built in some cases. So what I was just saying, a sag to span ratio leads to a certain force in a pillow. If I now write here, rewrite the formula, which was that the stress in the membrane equals 0.5 times the radius times the inner pressure, then you actually see that the span of the system isn't part of this formula. Nowhere in here does it say how far does this cushion span. And with membrane materials, if I look at this thing has a maximum span of 6 meters. And this one has a maximum span of, I think, 250 meters, something like that. Then you could imagine that if I can, with this formula, say I can calculate the radius that I need to build this cushion, then in this case, you know, the maximum curvature that you can put into it would be a kind of half circle. And then still the radius would be over 100 meters. Right? Whereas in this cushion, the radius that's defining the curvature here might only be like 10 meters. And now if you realize that the span actually isn't connected to the forces within the cushion, and we have a limited amount of membranes that we can build these with, then you could actually say, as of a certain span, I just simply cannot build these pneumatic systems anymore. So what they had to do is they had to add cables, which can take a much higher tension. And then the curvature, which you can see on this lower image, would appear between the cables. And then you're back down to a radius around 10, 20 meters. Right, and this is what you see in this graph. So this is actually radius in meter. And somewhere in here, you get a certain amount of pressure in the cushion, and that leads to a certain tension in the membrane. And then you can actually see that in these pneumatic systems, the freedom to choose form is actually super limited, because you need enough pressure in the cushion so you can outbalance outer forces. So if there's 6 or 0.6 kilonewton per square meter snow on it, then you need to put so much pressure into the cushion so it outbalances the snow. If you have a material that cannot take more than 1 kilonewton per meter, then you can immediately say, okay, I can only build a cushion that has a radius of 5 meters. And then that totally defines the shape. So in these pneumatic systems, they would be much more limited in the shapes that are possible to build. And this is why you then very quickly see in these mega stadiums that were predominantly built in North America, that quite soon they would add cables to support them. So a few more impressions, and then at the end I will now just look into branch structures and give a bit of an outlook into shells. These branch structure systems, they were mainly following the idea, how can I collect forces from a large surface on a minimum load path through compression only. The idea is to avoid bending. Bending forces need more material to be carried than compression forces. And the idea of only using compression or tension would then lead to this idea of how can I catch the forces within a surface on a minimum load path with compression only. And a lot of experiments were made, again, working with soap film, looking at these bifurcations between different surfaces and understanding what the angles are in this system, realizing that in these three-dimensional systems, they always end up having the same angle. And then also working with threads and weights being pulled onto them. So here simulating a surface load that's of the same magnitude. If you turn that around, so first organizing the bifurcations, and then with these loops, you could then find this minimum load path. So a compression force from here would find on the shortest compression only path its way into the support. There was a lot of studies then also dipping kind of chaotic assemblies of strings into soap, pulling them back out and studying these shapes, always trying to understand the relationship between these angles that would appear in these systems, and then developing from that a kind of shape grammar that you can build these systems with. And actually, because they're quite complex to realize, because these are totally three-dimensional systems, you only see very few realized structures. One of them is the airport in Stuttgart with cast nodes. They're cast out of steel, and then the individual tubes are being connected here. And then you can indeed see that at the top, the span of the roof between the points where it's connecting to this structure is always the same. So this span is nearly always the same. So you get a very, very optimally carried roof. Then if you say, so I have my entire roof and I'm splitting it into a series of secondary beams, and then I say I want all the forces to go down here, then they would kind of simply connect these forces with each other and then eventually lead them down into the ground. And then the next pillar would start here, and then this is how the system then develops. Right, and that today you can do that on a computer. You can quite simply, an easy method with Kangaroo is that you can just say, you make a strength goal, you connect all these lines, you try to minimize the length of these lines. And then you can say that in terms of forces, you have a ratio of 1, 2, 1, 2, and this is 1 and 1 and 2, 1 and 1 and 2. And then here we have 2 and 2 and 2. So here you have 6. So you can just always add up the forces that go into the system. If you put these values into a form finding program in terms of pre-stress or strength goals, then you end up with these shapes. And then you can vary them a little bit, whether they end up down here or here. You can play with these numbers a little bit. But that's the basic hierarchy principle that you can use for this type of form finding. Okay, and then at the end, a short look into grid shells. So the fourth subject that they were studying intensely at the IL. And what's quite interesting and what I always found super intriguing when I started working on my PhD is that they were built through elastic bending and they were form found with strings. So the form finding models were usually in the beginning always hanging chain models. And in the beginning of my PhD, I always argued, well, but yeah, they probably didn't form find them through bending because back then they didn't have computers to calculate that. And then I studied that a little bit more, and I can show you a few insights into that. But true to the institute and true to the entire work of Frei Otto, they would always try and derive these geometries with these really super finely built models. In this case, this is a model of Multihalle Mannheim, or here the very first grid shell they built in Essen as first a string model, and then already the mirrored version with these tiny pieces of wood. This is actually also a model photo. So in Frei Otto's house, he had his private house at the top of a hill, and then below he had another lab that was away from the institute, and they had this special setup with a table that they always put every model on, and they would always take photos of these models against the sky. So you see a ton of these model pictures which almost look like they're the real structure, but these are always models. This would be like maybe 20, 30 centimeters wide. So this is a tiny model, but they always had this way of taking photos against the sky. And then that actually became quite a popular way of taking pictures of your architectural models. And usually you see this tree behind it that maybe gives you some idea that there's something out of scale. This I will just mention. Enrique, you guys are probably explaining this, right? The campus method and these ways of finding grids on surfaces.
Campus?
Huh?
Campus method?
Yeah, exactly. So I assume that this will be studied in more detail in your course. Just saying again that the basic principle, what they were trying to do with these grid shells is that they would use, again, this idea of minimum. You can build a shell out of curved elements that you cut out of timber or where you bend steel, and then it's super energy intense and super material intense. But the cheapest building material is still a straight beam that can be transported really minimally, that can be produced really minimally. So they said, well, if form carries, if force and form are so highly connected, can we find shapes where we can elastically deform our elements into something that becomes so stiff that we can build a structurally sound system out of it? And now if we're elastically deforming the grid, then we also need a grid that is developable. So you can put it flat on the ground, and then you can push it into the 3D shape. And the only thing that changes is the angle between the elements. right? So you can see that down here, it has a different angle to over here. Sorry, I'm just clicking instead of drawing. And the method that they found is that a grid that is developable, or a kinematic grid that you can open, that you can deform and that doesn't block itself, works if the distance between the two members that are opposite each other have the same length. That's an observation that you can make. Now, if you're on a 3D surface, that's if you're flat, then it's quite easy to build. If you're on a 3D surface and you're trying to find that grid, which is developable, then you can just walk across the surface with a compass. You find the crossing points, and then that defines your grid. So you first have a surface, and then you back argue into the grid that you need to build the surface. So again, a super simple method that you can find just by arguing. Now, earlier on, I was saying that I was a bit confused when I first saw these grid shells, why they were using the hanging shape and not the bending shape. So this arch, which I'm drawing here at the top, is actually the result of bending a piece of wood. This arch, which you see below here, is the result of hanging a chain. And this here is a circle. So you can see that these three are totally different curves. And what I did as a quick study, I compared a circle, a hanging chain, and an elastica, so the bending curve, to each other. And I was just varying the rise to span ratio so that I get all these different shapes. And then you can see that in the beginning, up to a rise to span ratio of about 10–15%, then all three curves are almost matching. And then only above 30%, you see a clear difference between red, the hanging chain model, and black, the bending, the elastica curve. And I realized this, and then I was like super happy, said, wow, I just found out this cool thing. I need to talk to these people. Maybe they didn't know about it. And then this moment happens, which will happen to anyone in lightweight structures. You think you had an invention, and you talk to someone of the former IL people and say, yeah, Otto has drawn this graph in book 16 on some of these pages. I'm sure some of you have seen these books. They are just, don't know if you see my camera, they're just full of small hand drawings where everything that you can think of has been drawn by hand almost as one of the basic principles. And these books are so full and so resourceful that you can easily overread something like this. And at the time when we were building the first bending active structures at the University of Stuttgart, we actually visited Otto in his atelier and talked to him. This was in 2010. And we explained to him what we wanted to do. And I was super amazed. He was basically blind. So we could only explain to him through his imagination, and we could convey to him what we were trying to do. And then we were saying like, well, yeah, we can now, with this amazing FEM software, we can do this form finding. So we know exactly what the bending shape is. And then we actually want to build the geometries based on this bending shape. And then immediately, within seconds, he replied, oh, but you can just build a hanging chain model up to a ratio of about 30%. These curves are almost the same. And this really, really impressed me, because I realized that this, at the time, 84-year-old man, he had built so many models and was always there and always saw what's happening, that he had this straight away in his head. And these books are full of these kind of things. That was, for me, kind of almost the most impressive moment, where I thought in my PhD, after hours of sophistic simulation, that I found something quite interesting. And this guy just had it in his head, because they were building these models, and they could, through these very basic understandings, they just knew what was happening. And similarly, if you then try to find out what are the radii that I can work with, how far can I bend an element before it snaps? There's some relatively complex beam theory equations by Bernoulli or Timoshenko that can give you the relationship between elastic deformation and bending forces. And again, you can actually reduce it to a very simple formula, which says the minimum radius is the stiffness, the Young's modulus, times the beam height over 2 times the permissible stress. So this is how much stress you're allowed to put into the material. That you can just check in a textbook for timber, steel, aluminium, glass fiber. This is how stiff it is. Again, a number from your textbook. And then you can see that there's a linear relationship between the height of your beam and the minimum radius that you can bend it into. And again, with that very simple formula, you can then very quickly pre-dimension your elastic grid shells or whatever you want to build, find out what kind of shapes can I build with this material thickness and which ones I cannot build. And actually, if I remember correctly, I wrote in one of my first ISS papers, this must have been around 2010, I wrote this formula into it and explained how we were building that first pavilion, which we were visiting Frei Otto for, and where I was then first doing all these numerical theories behind it. I published a paper on this and put that into it. And I got an email by Enrique and Pep shortly afterwards. And they said, oh, wow, we're also researching into this direction. Thank you for writing down these formulas. We always thought that there were these relationships and can't recall. Cool for writing it down so clearly. For me, it seemed like a bit of too much praise for something that I'd just kind of taken from this Frei Otto way of explaining things in the most simple possible way. And that's actually what connected us. And since then, we've been visiting each other, doing research together and talking to each other. And I think I'll stop here. I won't go into the grid shell samples themselves because I'm sure that you guys will look into that in a lot more depth yourselves.
You're wonderful, Julian. Has been a bit long, but really, really mesmerizing. I think students will. I invite them to revisit the recording. So very briefly, anyone has a question? I do have one, Julian. I mean, wouldn't you have built the Olympia Stadium with timber?
Wouldn't I have built what?
Net? Build the Olympia Stadium just with timber laths. Could you have? I mean, there are so few, but really beautiful example of tension timber structure, right? Not like now the students are still in the Solemar swimming pool, for instance, and it's beautiful, no? When you take a fibrous material and you were saying, you were showing how timber can be even better than not steel. They are cables, okay, but do you think you could have built such a long span?
Do you know the photos of the Olympia Stadium underground?
Yeah, they are massively, blocks of concrete.
Yeah, I can. While I answer, I can very quickly try and find the the photo. So because they were building tension only, obviously it would be extremely high forces that they would have to anchor into the ground. Where is it? No, I think it's in a different lecture. I won't find it so quickly. But basically, I think what's happening here is one thing is that it's pre-stressed, and that already leads to a certain amount of tension that you need to anchor. And the second thing is that the shape that they were building carries forces by tension. And this effect that given the shape of the roof, no matter whether you build it out of steel and pre-stressed cables or whether you build it out of timber, it's always going to lead to the same force that you need to anchor.
Okay.
And you could only bypass this if you then change the shape and you lead to more shortcutting of forces because the bending of the timber works against the tension or something, but then you would end up with different shapes. But if you would say, I'm going to build exactly that shape,
no,
and I make timber strips and connect them, then that shape would carry the forces in exactly the same way. And it would lead to the same foundations. Whether you can build a shell with this mega span open edge, I think that would be pretty tough.
Okay.
Right? Because, yeah, you kind of need to shortcut it. Let me see if I can find, I think I've just found where I had it in some lectures. Because this was in Stuttgart, a huge debate about how sustainable is Olympia.
Yeah.
Right? Because of all of that. And they were taking that debate quite serious in trying to find better ways of reacting to that. Oh yeah, here we go. So where can I share the screen? All right, so this is on the side. This is actually not the mega arch. For some reason, I don't have the image in here.
Looks like a model, this picture, don't it?
Yeah, maybe it's cut and you can see more. No. So this is on the side where you have quite short spans, and then on the back here you have the large span across the stadium. Oh no, over here, and there you have an edge cable that spans over 250 meters. And to do that on this part, I'm sure the swimming hall you could build out of timber for sure. The seats above the stadium, tough. There's an image of one of the foundation points. That's how crazy it ends up. And then this actually led to a huge development into systems where you can shortcut tension and compression, the spokeswheel principle, where that eventually led to these kind of stadium roofs where all the forces are shortcuts. So none of them are anchored. And then you get these super light systems, right? This is the same as a bicycle wheel. Compression on the outer rim, tension in the inner. This is kind of slightly inverted, pushed into an oval that leads to higher buckling loads around the edges. That's why it's doubled up here. But it's basically the principle out of building a bicycle wheel. So
nice.